Hi everyone, this is Dr. Nuck, and today we're going to be learning about how to evaluate and graph logarithmic functions. In the past, every time I mention the word logarithm, most of the students just runs the other way. But I don't want you to. I really want you to like it and do not be afraid of logs if you heard bad things about it. So let's first go with the definition. The function f of x equals log base a of x is the logarithmic function with base a strictly greater than 0, x strictly greater than 0, and a does not equal to 1. And the statement y equals log base a of x is equivalent to x equals a to the yth power. I know this looks kind of overwhelming, but let me just try to explain the best I can in the simplest form. So in its simplest form, a log answers the question, how many of one number do we multiply to get another number? So for an example, maybe we can ask ourselves, how many 2's do we multiply to get to 8? Well, the answer is what? So we got 2 times 2 times 2 equals to 8. So we had to multiply 3 of the 2's to get to 8. So in this case, we say that the logarithm is 3. Now let's learn how to write this. So we write the number of 2's we need to multiply to get to 8 as log base 2 of 8 equals to 3. So basically, if we have 2 times 2 times 2 equals to 8, that's equivalent to log base 2 of 8 equals to 3. So if I write the left-hand side by using exponents, then we see that 2 to the third equals to 8 is equivalent to log base 2 of 8 equals to 3. And that is precisely what the formal definition is telling you. So if we go back to that formal definition that we wrote earlier, remember we had a to the y equals to x. I know that I'm kind of changing the orders a little bit. This is equivalent to y equals log base a of x. And we called the letter a in this case as a base. And then of course, the y is the exponent. So then when you look at the log base a of x equals to y, then this little a is the base, and then this y is the exponent. Alright, so now let's take a look at some examples. So example 1, convert to logarithmic form. So let's try to apply the definition to convert 5 to the 1/2 equals square root of 5 in log form. So let me just write down the definition. So we had what? A to the y equals to x is equivalent to log base a of x equals to y. So what we're asked to do here is we're going to be working from left to right, meaning given this, rewrite that in log form. All right, so let's take a look. So who's the base? Base is a, but our base is 5 over here. So we have a equals to 5. And what's the exponent? Exponent y is nothing but just 1/2. And who plays the role of x? Square root of 5. So keep that in mind, and let's rewrite this as, so this is equivalent to saying that log base a of x, which is square root of 5, equals to the exponent, which is 1/2. So we're done. All right, now let's take a look at another one. Let's try 1/2 to the x equals 1 over 16. So let me just write down the definition again. So what we're given is a to the y equals to x. This is equivalent to log base a of x equals to y. All right, so let me just, so on the left hand side, we still have an x flying around, so I don't want you to get confused with the definition of x. So let me just change the color a little bit. So our exponent here is going to be x. And then our base is 1/2. And our x value is 1/16. Oh, I think I forgot to circle this y as well. All right, so keep that in mind, then let's rewrite it. So this expression is equivalent to log base a, so a is 1/2. I don't know why I put the parentheses there, sorry. Log base a of x, x is 1/16, equals to y, which is the exponent. In this case, it's x. So I'm gonna box that for the answer. All right, now what I want you to do is pause the video and try part C, which is 4 to the 1/3 equals to cube root of 4. Please rewrite that in log form. All right, so let's take a look. So I'm gonna rewrite this definition until I memorize it. All right, so let's see if you got it or not. So I'm gonna try to rewrite this in a log form. So did you have log base a, base is 4, of x, which is a cube root of 4, equals to the exponent on the base, which is 1/3. So this is the answer. How did you guys do on this one? I'm hoping that you're kind of seeing the pattern here. Don't worry, we're gonna do more examples, so let's just do another one. So again, please pause the video and try this problem. All right, so I'm going to start. A to the y equals to x is equivalent to log base a of x equals to y. All right, so let's see what you got. So did you guys get this? So this is equivalent to log, who's the base? Base is 1/2 of x, which is 1/32, equals to the exponent, which is x. Did you get that one? All right, so this should be the answer. All right, now let's try example 2, convert to exponential form. So let's look at part A. 3 equals log base 4 of 64. So what we're going to do here is we're going to do backwards from example 1. So example 1, we were given the exponential form and we turned that into a log. Now it's the other way around. We're going to be given the log, but we need to turn that around into an exponential form. But regardless, let me write down the definition. So a to the y equals to x, if and only if, or equivalent to log base a of x equals to y. You know what? I don't know if I mentioned this or not. Probably not. I'm sorry. So this form is called the exponential form. And then this side, this form is called the logarithmic form. I'm just going to denote it as log form. So here what we're going to do is we're going to be given the log form and then we're trying to rewrite it in terms of an exponential form. I remember I had the most difficult time doing this, so this is how I remembered. So given the log form, right? If I want to write it in the exponential form, I went like this. Given log base a of x equals to y, this is equivalent to a to the y equals to x. I know it's really silly, but that was the only way that I could do it. So in this case, right, if we're gonna rewrite this in exponential form, all I had to do is, well, y is on the left hand side now, so I'm gonna go 4 to the 3rd equals to 64, and then we're done. But anyways, you can stick with whichever method that you want. Just look at the definition, determine who plays the role of a, y, and then x, and then you should be able to rewrite it. But here what we're going to get is 4 to the third equals 64. And this is going to be the answer. Alright, now let's try something like this. Example B, log base x of 1 equals to 0. So this is equivalent to x to the 0 equals to 1. And we're done. Oh my gosh, that's supposed to be an x, sorry. X to the 0 is 1. And that's all you gotta do. Alright, how about this? Why don't you try this one by pausing the video? And again, I'm pausing. I don't know why. Alright, so I'm gonna assume that you paused it. Let's do this. So here what we're gonna get is 10 to the negative 2 equals to 1 over 100. So let me write that. We got 10 to the negative 2 equals to 1 over 100. So there is that. All right, let's try something like this. Example 3, now we're gonna have to find the value of x. So part A, we're given log base x of 36 equals to 2. So somehow we need to come up with the base so that that base to the second power is gonna give us 36. So if I apply that looping definition, not the looping, the little loop that I was making earlier, so this is equivalent to what? X to the second power equals to 36, isn't it? So I'm going to rewrite this as x to the second is 36. Now can you guess what the value of x is? Yes, it's plus or minus 6, isn't it? Because if I apply the square root property, this implies that we're going to have x equals to 6 or x equals to negative 6. But here is the thing. Our base and the argument of the log cannot be negative. That's called a domain restriction. So meaning that little base x and what's in the parentheses cannot be negative. So in this case, we need to throw this guy away. So our answer is just x equals to 6. Okay, now let's try something like log base 1/2 of 1 over 8 equals to x. So now let's try to write this in exponential form. I apologize if I keep using the looping method, but you don't have to do it the way I do it. Just stick with the way that you feel comfortable with. But I'm comfortable doing it this way because this is how I survived intermediate algebra and when it came to logarithm. But anyway, so I'm going to rewrite this as 1/2 to the x equals 1 over 8. Alright, now our job is to find the value of x. So let me just first denote that. Do you see that 1 over 8 is same thing as 1 over 2 to the third, which is 1/2 times 1/2 times 1/2, right? Which is what? 1/2 to the third power is 1 over 8. So what I'm going to do is I'm going to rewrite this as 1/2 x equals to 1/2 to the third. Now since our base is the same, we can equate the exponent. So that implies that x equals to 3. So that's our answer. Alright, so would you like to try this one? Part C, log base 1/3 of 1 over 27 equals to x. Why not? Try this problem on your own and please tell me what you get. So I'm going to assume that you paused it and tried it. So let's get to work. So I'm gonna go 1/3 to the x equals to 127. Let me just rewrite it that way. 1/3 to the x equals to 1 over 27. Alright, so now our job is to try to rewrite 1 over 27 in terms of base 1/3. So let me just rewrite 1/3 x equals to, alright. So 1/3 to the what power is going to give us 27. Sorry, 1 over 27. Well, isn't it 3? Because 1 over 27 is same thing as 1/3 times 1/3 times the 1/3. So this is 1/3 to the third power. So I'm going to rewrite it as that. So therefore, our answer is x equals to 3 again. Did you get this problem okay? Well, I am hoping that you are getting hang of it. So if you are, let's take a look at another example. Now let's play this game. Example 4, find the exact value, of course, without using your calculator. So part A, what is the value of log base 5 of 25? So first, let me just write it like this. Log base 5 of 25 equals to x. So you can ask yourself, 5 to the what power is going to give us 25? Or simply, you can just go 5 to the x equals to 25 and then try to rewrite it. Now can you guess what that x value is? Yes, x must be 2, isn't it? Because 5 squared will give us 25. So therefore, our x must be 2. And that's our answer. Let's try log base 9 of 3. So again, I'm going to do the same thing. Equals to x. So the value of x is what we're looking for. So I'm going to loop it. 9 to the x. 9 to the what power is going to give us 3. So let me just rewrite it as 9 to the x equals to 3. All right. Now our job is to equate that base, which I forgot to do that for part A. Is it okay if I go back to part A real quick? I'm going to. So notice that I can write 25 as 5 squared. Now since bases are the same, so we can equate the exponent. That's why we got x equals to 2. Sorry for skipping that step. Alright, so now our job is this. Well, I need to try to rewrite 9 in terms of base 3. So let's try this. So 9 is same thing as 3 squared, isn't it? So we have 3 squared to the x equals to 3. Is this true? Is it going to, on the left hand side, is it give us 9 to the x power? I think so, because 3 squared is 3 times 3, and then we got the little x. All right, now remember what to do with these two exponents. Yes, we multiply them. So that's same thing as 3 to the 2x equals to 3, but do you see that there is that invisible 1 as an exponent on 3? So now since we have the same base, we can equate the exponents. So in this case, we have 2x equals to 1. So that means that x must be 1/2. And there you go. I mean, is that true? You can also check because look, is it true that 9 to the 1/2 gives us 3? I think it does because 9 to the 1/2, isn't it same thing as square root of 9? Well, square root of 9 is 3, so it makes sense. Okay, so now let's take a look at part C, log base 2 of 1/16. Do you want to try this one? I think you want to try this one. So please pause the video and try it. Alright, I'm going to do the same thing. So I'm going to start off with log base 2 of 1/16 equals to x. And then I'm going to ask 2 to the what exponent is going to give us 1/16. So now what we need to do is we're going to have to rewrite 1/16 in terms of base 2. Well, what do you think? 1/16, let me just work this as a side work. 1/16 is 1/2 to the what power? 16 is 2 to the 4th power, isn't it? And furthermore, if I have to write this in terms of base 2, this is same thing as 2 to the what power? 2 to the -4. Okay, so 1/16 in terms of base 2 is 2 to the -4. Alright, so let me try to rewrite this. We got 2 to the x equals to 2 to the negative 4. Well, we got the same base, so we can equate the exponents to get x equals to negative 4. How did you guys do on this one? That one was a little bit tricky, wasn't it? But hopefully you're understanding it now. And with that said, try this one too. Please pause the video and try to get the exact value of log base 2 of 1 over 32. Alright, so I'm going to start the problem as 2 to the what power is going to give us 1 over 32. Right, so now the game is I need to be able to rewrite 1 over 32 in terms of base 2. So let's see, what did you guys get? I got 1 over 32. How can I rewrite 32 in terms of base 2? So 2 to the 4th, no, that's not it. 2 to the 5th, that should give us 32 back. Alright, so now 1 over 2 to the 5th, I can rewrite it as 2 to the negative 5. So let me just rewrite this as 2 to the x equals to 2 to the negative 5. So x must be negative 5. And here's the answer. Did you get this one okay? Hopefully you are. And do not get discouraged if you're not getting it. You can always go back and practice more. Seriously, if I can do it, you can do it. Alright, now what we're going to do is we're going to learn how to graph the logarithmic functions. Now in the previous section, we learned how to graph the exponential function, and I'm hoping that you are comfortable with it. Because in order for us to graph the log function, it might be easier for us to convert that into an exponential function. Let's take a look at example 5, graph y equals log base 3 of x. Now, I'm going to convert this into an exponential form, which is 3 to the y equals to x. Because they're equivalent, remember? So I'm going to write it as 3 to the y equals to x. And now I'm going to make a chart. Okay, so I'm going to make the chart with y, and then 3 to the y equals to x, and then I'm going to express that as an ordered pair. Okay, so it doesn't really matter what value of y that you're going to choose, but I usually start from negative 2, negative 1, 0, maybe like 1, 2, and a 3. I think that's good enough. Alright, so let's take a look. When y is negative 2, we're going to have 3 to the negative 2, which is 1 over 3 squared, which becomes 1 over 9. So here, what we're going to get is, be careful, our y is the first number, and then the x is the 1 over 9, the second one. So here, our x comma y is going to be 1 over 9 comma negative 2. Now let's go with when y equals to negative 1, we're going to have 3 to the negative 1, which is 1/3. So here you're going to have 1/3 comma negative 1. And when y is 0, 3 to the 0 is 1. So you're going to have 1 comma 0. And then 3 to the first is just good old 3. 3 comma 1. And then 3 squared is 9. So we got 9 comma 2. And then 3 to the third is 27. So we have 27 comma 3. Let's plot some points. So let's first go with the ordered pair. When x is 1 over 9, y is negative 2. Oh no, x is, this is such a tiny grid, but alright, so maybe 1 over 9 is here, negative 2 would be here. Alright, now the next one is 1/3 comma negative 1, so maybe 1/3 will be here. There you go. And 1 comma 0. I got that one. Alright, and then 3 comma 1. Let me see. Let me just write down. This is 1, 2, 3, 4, 5, 6, 7, 8, and a 9. and then -1, -2. Okay, so now what's the next one? We just plotted 1, 0, so now it's 3, 1, 9, 2, and then I'm gonna go outside of the bound because 27, when x is 27, it's gonna be out of this page. But anyways, so this is what the graph's gonna look like. Let me just change the color of it. Now the log function, the tail end, which is this tail end, will never ever touch the y-axis. So the y-axis is become the vertical asymptote. So what we did here was we just graphed 3 to the y equals to x, but remember that's equivalent to y equals log base 3 of x. So precisely this curve right here is y equals log base 3 of x. Now remember when we learned about how to graph exponential graph, the key value for x was -1, 0, and 1, wasn't it? So pretty much same thing's going to happen, but in this case, since we had to rewrite our function y equals log base 3 of x, our x and y are kind of swapped around. But regardless, let's take a look at this, and this. So this is when y equals to -1, 0, and a 1. So notice that our base is 3, isn't it? So we are given our base is 3. So when y is -1, we have 1 over the base, which is 1/3. When y is 0, it's always going to be 1, 0. And then when y is 1, our x is nothing but the value of the base. So keep that in mind, and let's generalize this. Alright, so what I did here was I just listed out the key points. Remember the key values were 1 over the base, 1, and then the base itself. So the base is a here. Alright, so then for sure our graph must go through 1, 0, as we learned in the previous section. And then when y is -1, it's going to be 1 over a. Remember, for the previous example, when y was -1, it was 1/3, and 3 was the base. So here, this point right here will be 1 over a, comma, -1, and the first point that we jotted out is 1, 0, and then next one is going to be a, 1. Alright, so this is the general property of the graph of y equals log base a of x. Now let's write down the properties of y equals log base a of x. And again, a must be strictly greater than 0, so is x, and then a cannot be 1. So let's first go with the domain. The domain is the set of all x values where the function is defined. So again, the tail end, the left tail end of the graph is never ever going to touch that y-axis. So it's never going to reach when x equals to 0. So here our domain is going to be open 0 all the way up to infinity. Now next is the range. Range is the set of all y values where the function is defined. So when you look at the range, you're going to have to look at the graph bottom upward. So towards the bottom, this graph starts from -infinity, and then it's going to keep going up and up and up very slowly but surely. So the range is going to be all real numbers, which is from -infinity to infinity. And this graph has the x-intercept. X-intercept is where the graph is going to touch or crosses the x-axis. So in this case, we got an x-intercept at x equals to 1. So here, I'm going to have 1, 0. Now, what about the y-intercept? Does the graph ever touches or crosses the y-axis? I don't think so. Again, because of that tail end, the bottom tail end of the graph is never going to touch that y-axis. So there is no x-intercept. So I'm going to write this as none. And where are the key points? Well, key points are at 1 over a comma 1, and then 1 comma 0, and then a comma 1, where a is the base. Now what about the asymptote? Well, we have a vertical asymptote at x equals to 0, which is same thing as the y-axis. So here, I'm going to write it as y-axis is the asymptote. But in order for us to write the equation of that line, is nothing but x equals to 0. So that's the equation of a line, by the way. So this is the property of y equals log base a of x when a is greater than 0. Now let's talk about what the graph of y equals log base a of x is going to look like if a is between 0 and a 1, such as maybe 1/2, 1/3, 1/4, and so forth. So let's take a look at example 6, graph y equals log base 1/3 of x. So again, let's do the same thing by making the chart. But before we do that, let's make this into an exponential function. 1/3 to the y equals to x because they're equivalent. And we're going to make a chart. Okay, I'm going to pick the same values as I always choose, -2, -1, 0, 1, 2, and a 3. All right, let's do it. So when y is -2, we have 1/3 to the -2. Well, isn't this same thing as 3 squared, which gives us 9. So again, remember, our y is listed first. So here, ordered as an ordered pair, we got 9 comma -2. All right, now let's go with when y is -1. So we got 1/3 to the -1, which is 3 to the first, which is 3. So we have 3 comma -1. Then y equals to 0, we got 1/3 to the 0, which is just 1, 1 comma 0, and then 1/3 to the first is 1/3. So here you're going to have 1/3 comma 1, and then when y is 2, we're going to have 1/3 squared, so this is 1 over 9. So we got 1 over 9 comma 2, and when y is 3, you're going to have 1 over 27. Super duper tiny number, but here you're going to have 1 over 27 comma 3. All right, let's plot some points. So let's go with the first ordered pair. When x is 9, y is -2, and 3 comma -1, and then 1 comma 0, and then the next one is when x is 1/3, y value is 1. So 1/3 might be like here. All right, and then 1 over 9 comma 2, so 1 over 9 is closer to the y-axis than 1/3, so let me see. Then when x is 1 over 27, even more closer to the y-axis, it's going to be, y value is going to be 3. So it looks like our graph is going to look something like this now. Now this time, the left tail end of the graph will never ever touch the y-axis. So this is the graph of y equals log base 1/3 of x. All right, again, we're gonna circle the key points, which are when y is -1, y is 0, and then y is 1. So in this case, our base is 1/3. So when y is 1, do you see that we're going to have our base? So let me just call base a. Then here you're going to have a comma 1, and then 1 comma 0 is always 1 comma 0. So that means 3 comma negative 1 can be written as 1 over a comma negative 1. Keep those key points in mind because we're going to now graph y equals log base a of x when the base a is between 0 and 1. Alright, let's graph this out. So what I did here was, again, I just jot down the key points. Now remember that from the previous example that we just did, our a was 1/3, wasn't it? So actually 1 over a is going to be bigger than a in this case. So keep that in mind. But anyways, so if I have to plot this, when x equals to a, it was at 1. Wasn't it? So we had what? 1/3 comma 1. So that's that point right here. So I'm going to call it as a comma 1. And then good old 1 comma 0. And then 1 over a comma negative 1. Now let me connect those dots. And here it is. So this is the graph of y equals log base a of x when a is between 0 and 1. Okay, so let's summarize the properties of y equals log base a of x when a is between 0 and 1. Alright, so let's start out with the domain. So the domain here again is from 0 to infinity, but remember, that upper tail end of the graph is never going to touch x equals to 0, which is the y-axis. So in this case, our domain is open 0 up to infinity. And the range is the same thing when a was strictly greater than 1. So in this case, our range is also from negative infinity to infinity. And where's our x-intercept? X-intercept is where the graph's going to cross or touches the x-axis. So in this case, graph crosses the x-axis at x equals to 1. So in this case, x-intercept is 1 comma 0. Alright, now let's go with the y-intercept. Do we have any y-intercept? No, because that tail end of the graph is never going to touch that y-axis. So none is that answer. And what's the next one? Key points. Again, those are a comma 1, 1 comma 0, and then 1 over a comma negative 1. I think I forgot to write that on the graph, so let me just do that. So this point is 1 over a comma negative 1. Now where is that asymptote? So it looks like we got a vertical asymptote at the y-axis, which is x equals to 0. That will be the equation of the line. So I'm just going to write it as y-axis. Now equation of the line is going to be at x equals to 0. Again, this is an equation. And if you look at this graph, right, is it increasing, decreasing, which one? Well, when you read the graph, you're going to have to look from left to right. So notice that this graph is falling, therefore it's decreasing. So I'm going to write it as graph is decreasing. Alright, now let's talk about a very, very important fact. So the fact is this. As we recall, f of x equals a to the x. Remember, that's the exponential function. Now, we also talked about the inverse function of f, which is denoted by f inverse of x. Well, guess what? The inverse of exponential function a to the x is nothing but log base a of x. So a to the x and log base a of x are inverse functions of each other. Let's recall the graph of exponential function and the log function. So in blue, I'm going to graph y equals a to the x, which is the exponential. I don't know if you remember this or not, but no matter what, it better go through 0 comma 1, negative 1 comma 1 over a, and then 1 comma a. And the graph went like this. I'll just make this dot fatter. There we go. Now let's graph y equals log base a of x when a is greater than 1. So no matter what, it has to go through 1, 0. We already talked about that. Where can I write that? I'll just write it 1, 0. And then a, 1. And 1 over a, negative 1. And the graph is going to look something like this. As you know by now, my drawing skill is so bad, but let me just try to graph y equals to x. Y equals to x is that straight line that's going to go through 0, 0, 1, 1, 2, 2, 3, 3, and so forth. Do you notice something? So if I fold this graph along the line of y equals to x, do you see that the blue graph and orange graph, they're going to match each other? That's exactly the property of inverse function. So they are mirror image at the line y equals to x. Now let's take a look at y equals a to the x and y equals log base a of x when a is between 0 and 1. Let's start drawing the exponential function. So for sure, I know for sure that the exponential function must go through 0, 1. And then, I forgot to write the grid right here. All right, now when x is negative 1, it's going to be at 1 over a. And when x is 1, it's going to be at a. So if I connect those dots, let me see. All right, so this is the graph of y equals a to the x when a is between 0 and 1. Now let's try to graph out the log function. So it does have to go through 1, 0, that I know. Other key points are at a, 1 and 1 over a, negative 1. All right, let me see if I can draw this out. All right, so this is y equals log base a of x when a is between 0 and 1. Now let me draw that straight line y equals to x. So this is the graph of y equals to x again. Now, do you see the same thing's going to happen? If I fold this graph along the line of y equals to x, those two graphs are going to match up. So again, this is going to be the mirror image of each other along the line of y equals to x. So that's the properties of the inverse functions. No matter what kind of inverse function that you're given, it's always going to be symmetric with respect to the line y equals to x. It does not have to be just the exponential and a log. It's always true for any other functions as well. All right, now let's talk about this very, very important function, which is called a natural log function. So the function f of x equals ln of x is the natural logarithmic function with base e. By the way, e is approximately equaling to 2.7, but that's just an approximate value. And then again, the argument of the ln has to be greater than 0. So basically, if I have a log base e of x, this is by definition ln of x, just the notation changes. So if I write y equals log base e of x, this is true if and only if, or equivalent expression was, remember, e to the y equals to x. So we're going to have e to the y equals to x. But remember, log base e of x was notation-wise, it's ln of x. So that means that given y equals ln of x, this statement is equivalent to e to the y equals to x. So y equals ln of x is exactly the same thing as log base e of x. It has just a special fancy notation, and that's all. Now there's another one, not as fancy though. It's called the common log function. The function f of x equals log of x is the common log function with base 10. So notice that we usually have that little base attached to the log, right? But if it's not written, you're going to have to assume that there is an invisible 10 sitting there. So here, log base 10 of x, by definition, this is just log of x. Now, if I want to write this as an equivalent statement in terms of exponential form, then let me just go like this. Let y be log base 10 of x. Now, what is the equivalent statement? This is true if and only if 10 to the y equals to x, isn't it? So we got 10 to the y equals to x. But log base 10 of x is just log of x, so notational wise, therefore y equals log of x is equivalent to 10 to the y equals to x. So these two functions are very special because I'm not sure if you have looked at your calculator, but the only log function keys that you should have are ln of x and log of x, meaning there is no key for log base 2 of x or log base 5 of x. So you're probably wondering, well, what's going to happen if I was given log base 2 of 3 or something like that? I cannot punch that in a calculator. Well, there is a thing called change of base formula, which we'll get into that later on. Now, our next topic is to solve the log equations now. So let's get started. Example 7. Solve log base a of 49 equals to 2. Later on, we're going to be learning more properties of the log, so you don't have to go through the formal definition to solve an equation. But for now, we only know the definition, so let's use that. So first, I'm going to write this in terms of an exponential form, which is a to the second power equals to 49. Now, how do I solve for a? Well, we need to apply the square root property. So here, what we're going to get is a must be plus or minus the square root of 49, which means that either a is positive 7 or a is negative 7. But again, our base and the argument of the log, which is what's in the parentheses, they cannot be negative nor they cannot be 0. So in this case, we need to eliminate the negative value, and then we just keep the positive side of a. So our answer is a equals to 7. So we could also check actually. So check. Is log base 7 of 49, is that going to equal to 2? I think so, because if I loop it around, you're going to have to ask yourself, is 7 squared equals to 49? I think so. So it makes sense. Now let's try ln of x equals to 3 solve for x. Now, if you are not comfortable with ln, just remember that ln is nothing but log base e. So if you rewrite this, right? If I rewrite this as log base e of x equals to 3, do you see that this is equivalent to e to the third equals to x? Now remember, e is a number, so e is approximately 2.7. So here, we're done with the problem. So basically what we're going to get is our x value is going to be this crazy decimal value of e to the third. So this is all we got to do. Do you want to try one? I think you're ready. So as part C, log base A of 64 equals to 3, solve for A. Pause the video and try this on your own. Okay, I'm going to start this problem out with the same way. I'm going to make this into an exponential form. A to the third equals to 64. All right, now I'm trying to solve for A, so I need to get rid of that exponent of 3. So who's going to kill it? Cube root. So I'm going to take the cube root on both sides. And this will give us A equals to cube root of 64. All right, we still need to simplify, so let's just do this. What times what equals 64? 8 times 8. And 2 times 4, 2 times 4, 2, 2, 2, 2. So 64 is 2 to the what power? How many 2's do we have? 1, 2, 3, 4, 5, 6. 2 to the 6. All right, so therefore, let me just bring this over here. So our A is the cube root of 2 to the 6, which is same thing as 2 to the 6 over 3, which is 2 to the second power, which will give us 4. So therefore, our answer, A, is just good old 4. Did you get this problem okay? If not, catch your mistakes because that's the most important part. Alright, so let's try another one. ln of x equals to 9, solve for x. So again, please pause the video and try this on your own. Okay, I'm going to start the problem. Now, I can't remember anything except for the fact that log base e of x is ln of x. I'm just going to rewrite it as log base e of x equals to 9, and I'm going to loop around. So this is equivalent to e to the 9 equals to x. Are we done? I think so, because look, again, e is a constant, e is a number. So number to the 9th power, whatever that is your exact answer. So, boom, we're done. Okay, let's increase the level of difficulty just a little notch. Now let's try to solve log base 2 of 3x minus 5 equals to 4. Do not panic. All you have to do is try to write this as an equivalent statement in terms of an exponential form. So here, isn't this same thing as 2 to the 4th equals to 3x minus 5? That's all you got to do. So ready? So this is equivalent to 2 to the 4th equals to 3x minus 5. And then our job is to solve for x. Now, 2 to the 4th is 16 equals 3x minus 5. So here we're going to add 5. Then what do we get? 21 equals to 3x. Now divided by 3 on both sides. So that implies that what? X is 7. Now, before you box that for your final answer, remember the argument of the log cannot be negative. So you should double check. Argument of log is what's in the parentheses actually. So if I plugged it in 7 in place of x, let me see. If I plug this into here, would it give us a positive value? Whatever that's in the parentheses, is it positive? Answer is yes. So in this case, we get to keep x equals to 7 as a solution. You know, from the past examples, I forgot to put this in a solution set notation, but if I do that, answer will be the solution set is 7. Sorry about that. All right, now let's take a look at another one. So let's call this one was A, example A. Let's try something similar, which will be example B. Let's try to solve ln of e to the 3x equals to 6. So again, if you don't like ln, remember, ln is nothing but log base e. So if you want to, just replace it. So here, this is same thing as log base e of e to the 3x equals to 6. So then if I loop around, what am I going to get? E to the 6 equals to e to the 3x. So this implies that we got e to the 6 equals e to the 3x. All right, look, we got the same base, so all you have to do is equate the exponents. So this implies that, oops, sorry about this, 6 equals 3x, so that implies that dividing by 3, x must be 2. All right, now before I box it, I'm going to plug that 2 into the argument of the log base e or ln to make sure that what's in the parentheses is positive, which means the argument is positive. Well, we got e to the 3 times 2, which is e to the 6. Definitely that will be positive because remember, e is approximately 2.7. So we get to keep this one. So maybe I should write that in the solution set is going to be 2. All right, let's try another one. Why don't we pause the video here, and what I would like for you to do is try this problem on your own. So I'm going to start this problem with 3 to the third equals 4x plus 3. All right, so what's 3 to the third? 27 equals 4x plus 3. Now, minus 3, what the heck is that? 24 equals to 4x. Now, dividing by 4, our x is 6. Now, before we box that, let's check to make sure the argument of the log is positive. All right, so if I plug that x equals to 6 into what's in the parentheses, 4 times 6 plus 3, it's definitely a positive value. So he's a keeper. So therefore, our solution set is 6. Did you guys get this one okay? I am hoping that you did, but if you didn't, just go back and just find out where you went wrong. Let's do another one. ln of e to the 4x equals to 4. So please pause the video and try this problem on your own. All right, so I'm not too comfortable with ln, so I'm going to write it as log base e is precisely our ln. So here what I'm going to do is write ln in terms of log base e of e to the 4x equals to 4. By the way, you don't have to do it this way. If you know the definition, just go straight through, okay? But anyway, so this is same thing as e to the 4th equals to e to the 4x. All right, do we have the same base? Yup. So in this case, we get to equate the exponents. So we have 4 equals to 4x. So that implies that x is 1. Again, before we get too excited, make sure that the argument of the ln is going to be positive. So if I replace x in place of x, we get e to the 4 times 1, which will be positive. So he's a keeper. So therefore, solution set is 1. I feel like I'm torturing you by doing so many examples, but remember, math is all about practice. And I really want you to like log. I don't want you to run away from it. That's the only reason why I'm going through a bunch of examples. So please don't hate me. But anyways, I'm going to stop here. So again, if you have any questions at all, please let me know. And once again, good job you all. I'm very, very proud of you.